the OFDM actually, it is like your normal modulation technique, maybe AM, FM, TM, BPSK. These are all single carrier modulation techniques, right? So here the incoming data stream is modulated over a single carrier. But as I said earlier, when we want to improve the data rate, so we have to send your signals at a faster rate. When you are sending the signals at a faster, lower sampling time, no, sorry, lower symbol time, maybe 1 nanosecond, 1 microsecond, then there is a lot of other pulses are also joining into the communication channel because of the multipath communication. There is always an intersymbol interference, a severe intersymbol interference. This is happening because of your nature of your channel. That is, it is coming under a frequency fluctuated channel. Okay, so to avoid that one, we want to communicate in a normal way, normal communication. We want to do it in a normal flat fading channel. So what is the flat fading channel? The flat fading channel is irrespective of all the frequencies, whatever you are sending, it gives the same uniform distributed signal across your channels. So that means your channel is flat during your entire band of operation. But whereas when you are covering to the high frequency bands, the channel is not flat. It becomes frequency selective channel. So this frequency selective channel, I cannot go with your frequency selective channels because it is creating a lot of interference. So to avoid this one, still we want to go with a narrow band, but the same bands, maybe the multiple times over the, I am having a huge bandwidth. So this huge bandwidth is divided into smaller bands. In each band, I will parallelly send my information. That's what I am interested in. Okay. So that comes under OFDM, orthogonal frequency division multiplexing. So this is actually a multi-carrier modulation technique. So this employs some carriers, allocated bandwidth, and convey the source to the destination using many of the formats of BPSK, QPSK, or QAM. So this orthogonal frequency division multiplexing is a special case of multi-carrier modulation scheme. So in which high data rate stream is actually split into small data rates, and it is OFDM is actually to avoid this frequency selective fading, it is taking flat fading communication, right? So this OFDM is actually having a problem by converting the entire frequency selective fading channel into a small flat fading channel. We know what is a wireless communication. We'll receive the signals through multipath communications. And I am giving an equation to my multipath communication as each path is coming through a different amplitude and different delays. So alpha i's and tau m's are delays and amplitudes of my multipath communication. So this multipath communication actually will distort the waveform of a given signal. So if you look at the diagram of a frequency selective fading, because of this large delay spread present in my channel, I am receiving different gains from through multipath communication. One is at 2 seconds, two is at 2.5 seconds, another one is at 3 seconds. So this is my different gains. When you add up all these things, there may be a possibility of destruction or obstruction, like destruction in the sense the whole signal is summed up and coming to a zero value, or it maybe gets amplified. Okay. So these problems, then how to tackle all these problems in frequency selective fading channels? We use the orthogonal frequency division multiplexing, OFDM. So this is actually taking different carriers of F1, F2, F3, F4, and the peak of the each signal actually coincides with the trough of the other signals. Okay. So generally we know what is orthogonal frequency division multiplexing. If you have two waveforms, suppose S1 of t and S2 of t, and if you multiply this S1 of t and S2 of t, integrate over that period of time, then those signals are giving me the output as 0. That is orthogonality. And we know what is orthonormal. Orthonormal in the sense unit energy. Suppose each signal is having a unit energy signal and it is normalized, we'll get the orthonormal basis functions. So then you may ask some questions regarding what is the difference between earlier because we have earlier we have used a frequency division multiplexing. Through this frequency division multiplexing, we used to accommodate many number of users into the communication channel. See, this is same as OFDM is same as your frequency division multiplexing, or it is something else. Okay, so I would say that it is something different from the previously used frequency division multiplexing, because there is a large saving of bandwidth. So if you use, can you hear me, sir?
Yes, ma'am.
So if you
Yes,
use
sir.
the frequency division multiplexing, I have to use guard band between the channels. But whereas in OFDM, orthogonal frequency division multiplexing, we don't use guard band. We just place the carriers orthogonal to one another. So because of that, we are saving a large bandwidth in my spectrum. So when there is a large saving in the bandwidth of my spectrum, I can accommodate, even I can send more number of data at a faster parallel transform. So this design, how do you design this OFDM transmitter? So generally what we do, we take the bits, and while designing the OFDM transmitter, we need to consider how many number of subcarriers to transmit the given data signal. Okay. Suppose I want to transmit in my QAM format or my QPSK format. So QPSK format, in the sense it takes 2 bits at a time. Okay. I use maybe 10 number of carriers. So these 10 number of carriers, each carrier takes 2 bits because it is a QAM, it is a QPSK format. So 10 into 2, that means 20 bits. I have to wait till 20 bits of time. And these 20 bits are mapped according to my constellation diagram. Then they'll send across my all the subcarriers. So I will show you the diagram, how we are transmitted using orthogonal frequency division multiplexing. Okay, so this YFDM signal, just I'm quickly going through the slides because we need to complete the other modulation schemes as well. And also one student, one faculty asked for OTFS. I'll give you a brief introduction to the OTFS. So just finally I'm going through my block diagram. So we take the data stream and we'll wait according to your modulation scheme. We will wait how many carriers you want to use. I want to use some k number of carriers. Okay, I have a huge bandwidth. I divided by that bandwidth by some k users. So I divide the bandwidth for k number of users, k number of data streams. So my data, my signal, that is the carriers are F0, F1, F of n minus 1, like that they are going on, F of k n minus 1. And I take the data. We'll wait till serial to parallel conversion, because my QPSK format or a QAM format. So if I'm in this example, suppose I'm taking 4 carriers and my constellation diagram, what I am using is QPSK. So in the QPSK, each carrier can take 2 bits at a time. Okay. So 4 into 2, 8. So till I arrive, till the transmitter is giving 8 bits, I'll wait at this point, serial to parallel point. Then these 8 bits are given to each of the path of S0, S1 and S of n minus 1. They are mapped. According to that, they are mapped. And suppose QPSK, the first data stream D0 equal to 0, 0, then it is mapped to A plus J beta. Then D1, suppose it is 1, 0, then it is mapped to minus A plus J beta. So like that, that amplitude is multiplied with sine 2 pi F naught of t. Then we summed up all the values, we'll transmit the signal over the air. This is general principle everyone knows, okay? So this is how suppose if I am doing a BPSK modulation scheme, my data is coming in at different intervals of time, T0, T1, T2, T3, and I'll wait serial to parallel converter, because I'm using D1, D2, D3, 4 carriers. So onto these 4 carriers, I'll port my data symbols. I'll port my data symbols using a BPSK stream. And these are all multiplied with sign carriers. So different sign carriers. And we sum up all the values we send across my OFDM modulator. And next instant of time, some other signals are coming. The 4 signals are coming, and we'll multiply those 4 signals with different carriers We'll sum up all the values, we send over the OFDM transmitter. Okay. If it is a QPSK, then I take two different intervals of time. Those data streams are combined as a symbol. Then the symbol is multiplied with my sign, and accordingly they are multiplied with different timing intervals. So then they will be modulated onto my OFDM carrier. So this OFDM carrier, actually we can represent this OFDM signal as your data stream multiplied by a carrier, sine 2 pi fn of t, right? So this can be easily represented using your known principles of your Fourier transforms. So actually we know very well that Fourier transforms break a signal into different frequency bins by multiplying the signal with a series of sinusoids. That is, if I have a writing pad, I would have explained you in a nice way, in a better way, because it's not allowing me to use my iPad. Okay, no problem. We have to adjust with this one. So this actually essentially translates the signal from time domain to frequency domain. Or else I'll try to see with this notepad. Okay, but it takes time to draw the diagram. Okay, so we use IFFT and FFT as instead of generating independent carriers in the transmitter and the receiver, directly we can use the principle of IFFT block and FFT block at the receiver and the transmitter. So how it looks at the receiver and the transmitter. So if you use an FFT in frequency domain, my signals multiplied by sine and cos, right? So this is the representation followed by following the FFT equation. Similarly, IFFT equation, I'm using a frequency domain signal and they are multiplied by sine and cos. This resultant will give you a time domain signal. So in my transmitter and receiver, I can use these principles. There is a difference in the second equation. Actually, it is k equal to 0 to n minus 1, the IFFT equation, not the n. There is a printing mistake. The first equation is n equal to 0 to n minus 1. So I can use these orthonormal basis functions as your modulators. That is, we can replace the modulator using your IFFT and FFT block, right? So this IFFT, FFT, actually they behave in a dual way. So these are all, these blocks are also we can interchange. And if you look at the answer is, these IFFT and FFT equations also, they come in handy in implementing and also in the conversion process. We can eliminate the individual sinusoidal multipliers required for the transmitter and receiver side. So the same constellation diagram, what we have seen earlier, a block which eliminates your generation of multiple carriers, that is sine of F0, F1 and F of n minus 1 and so on and so forth, can be simply replaced with an IFFT block at the transmitting end. Okay. Similarly, at the receiving end, I can use an FFT block. It is an inverse operation. So I use the FFT block to remove, to translate your data stream into your normal BPSK PAM or PAM or BPSK format. We'll pass it through a parallel to serial converter. Finally, we can estimate what we have transmitted, that is D0, D1 and D of n minus 1. So these are all principles as of now, what I am saying. Everyone knows what is a OFDM. Okay. So, and also there is a role of cyclic prefix. Yesterday I talked about the cyclic prefix. So this is actually because of the non-ideal channel. There is some delay dispersion will happen in your communication channel. Because of this, there is a chance of intersymbol interference. And also on each subcarrier channel, due to this pulse overlapping, suppose there is a pulse overlapping because of this non-dispersive channel, there is always a chance of intersymbol interference and intercarrier interference due to the non-orthogonality. So, for example, if you generate sine 2 pi f naught of t, then sine 2 pi f naught of t plus some delta t. So, if these two multiplications, if they are not becoming zero, that means they are not orthogonal. So when they are not orthogonal, there is always chance of inter-carrier interference. So this also happens in OFDM. So to avoid this to avoid this inter-symbol interference, not the inter-carrier interference, to avoid the inter-symbol interference, we use a cyclic prefix. So we use some amount of cyclic prefix, that is what we are transmitting exactly at the beginning of your frame. Also, we'll add some content at end of the frame. Okay. So that is the way when you are decoding your signals, I can show you the diagram. So if you look at this one frame of data, that is a symbol energy spread across, actually we are transmitting n data streams, but we are also adding NC chip bits extra. So these NC chips are nothing but the last values of your data stream are added at the beginning of your cyclic prefix. So this is an additional redundancy we are keeping at the front of your frame. So then what is the advantage if you add this redundancy at the front of your frame? So when I am receiving, if there is an inter-symbol interference, because I know very well that the last part is joining with the first part. Okay. So what I do, my idea is I don't decode this last part, or I don't decode the first part of my frame. I start my decoding only after the cyclic prefix. So that's where I can avoid the inter-symbol interference in OFDM. And if you look at the total block diagram of the OFDM, that is the constellation diagram. From the block diagram of OFDM, after addition of the cyclic prefix, we can see that only the extra addition to this one is we have added a cyclic prefix at the end of the frame. Okay. So we have added a cyclic prefix at the end of the frame. So suppose if you are sending x0 to x of n minus 1, we'll add an additional numbers, that is x of n minus 1 to x of n minus ncp data bits additionally at the cyclic prefix. And we remove the same cyclic prefix. After that, we'll send those signals to the FFT block and we do the frequency equalization, we do the constellation demapping, and we go to the parallel to serial to parallel decoding scheme. Okay, so the key ideas behind adding the cyclic prefix is actually we are converting a linear convolution into a cyclic convolution. We know what is linear convolution and what is cyclic convolution. So linear convolution in the sense when you convolve two signals, suppose two rectangular signals, the convolution between these them will result into a triangular waveform. Okay. Similarly, if you are convolving a long signal with a short signal, then generally the time duration of your convolution will be the two signals sum plus some extra bit, that is 1. Suppose x and y, okay, m and n, then m plus n plus 1 data bits will be seen at the output of the convolution. But whereas in circular convolution, we are moving in a modular form. So we come back to the original shape. That is what the circular convolution we do in OFDM. So this helps in combating ISI and ICC. Okay. So what are the other advantages of OFDM? So this permits actually we can send densely packed and overlapping subcarriers, and also it's spectrally efficient transmission scheme. Why it is spectrally efficient? Because we are saving some bandwidth, right? Because if you use the frequency division multiplexing, we have to always leave some parts of the guard band, whereas in OFDM, we are not leaving any guard band interval between the carriers. We are using orthonormal subcarriers. So spectrally, it is more efficient. And also, the another most important advantage is digitally it can be implemented. That means it is fast and efficient signal processing scheme. And also it supports different modulation schemes based on the channel conditions. we can avoid any linear, any equalizers as well in this communication. So currently we are using this OFDM in LTE, LTE advanced, DVB, T by 2 terrestrial telecommunication, as well as 802.11a and 802.11g, 11n, 11ac, 11ad. In all these wireless standards, currently we are using OFDM. And also in WiMAX, that is worldwide interoperability for microwave access. LTE advanced and 4G mobile phone standards also. Currently, we are using OFDM transmission scheme. And also, as per the present scenario, the standards given by IMTT 2020, they're also given a green signal to use the OFDM even into the 5G communication. Okay. So with this, just I have given a brief introduction to the OFDM because I am quickly rushing through the slides. Then, if you want to ask me some questions in OFDM, you can stop me in between. If you have no questions, then I'll go to the next presentation.
Good afternoon, ma'am.
Yeah.
Ma'am, is the size of IF50 and subcarriers, number of subcarriers selection need to be same, ma'am?
Yes, need to be same because you are using endpoint FFT, right? So in the
Yes, yes.
endpoint FFT, suppose if you take an FFT signal n equal to 0 to n minus 1, you'll use your X of n, that is your data symbols, right? And e power j 2 pi FCT, that is your
Yes,
FFT equation. FCT in the sense you have to translate into a digital domain. So it is actually e power j 2 pi some k by n and small n.
yes.
Okay. So then how many number of subcarriers you are using and what is your data strength? That must be matching. Otherwise, I cannot accommodate all my symbols into my FFT block. So that is always necessary.
Okay.
So any other doubts?
Yes, madam. In chat box, one participant raised one doubt.
Okay.
Sir, Hanumantarao sir, are you there? Okay. Which constellation mapping is better, QPSK or QAM? Why?
QPSK, QAM. So the basic modulation schemes. If you have studied about the different modulation techniques available in our communication, digital communication. So as I said, if you go for a BPSK, from BPSK, if you go to the QPSK, from QPSK, if you go to the QAM, what is the advantage we are gaining from one modulation to the other modulation? So BPSK, the distance wise, they are separated, right? One is on the right side, another one is on the right left hand side. And also we have derived the probability of error equations. Like I can show my one of my note. In this pad, I could not open. Okay, advanced digital communication. ADC lecture notes. Okay, right. I'm just giving quickly reviewing what is the probability of error derived for BPSK case. So if you see that the probability of error of a BPSK case is Q of mod of S by 2 sigma. S means your transmitted signal distance. Okay. This is the probability of error for BPSK. Similarly, if you go for QPSK scheme, I can show you how we have derived for the QPSK scheme. Finally, we have derived for QPSK is my detection scheme. So it's a very lengthy process, right? So for channel 1 and channel 2, finally we have derived the QPSK bit error rate is 2 times EB by N naught, root 2 times EB by N naught. Okay, and for BPSK also we have, I said it is mod of S by sigma. Mod of S by sigma means energy of your pulse. So that is EB by N naught. EB by N naught. So what we are understanding that the probability of error is an argument of your Q function. And when the argument is increasing, the probability of error, because it is inversely proportional. The Q function is a waterfalling nature. So when Q of something X, Q of X, if X is more, the probability of error is less. If X is less, the probability of error is more. So in that case here for QPSK, I am getting 2 times. Whereas for BPSK, I am getting only single time. That is root EB by N naught. So which probability error is more? The first one or the second one? Sorry, QPSK, I am getting EB by N naught. So final, I can show you the final probability of error. This is my probability of error of my QPSK. Because one channel only I showed. So for QPSK, I am getting 2 times Q of something, whereas BPSK, I get only Q of the internal part of 2 of EB by N naught. So naturally, when you are keeping more number of points in the constellation diagram, the probability of error is also going to increase. So if you ask from BPSK to QPSK to QAM, naturally the distance between the points is very less. So your detection area is also going to reduced. So because of that, we are getting a huge amount of probability of error. So that depends. If you use QAM, if you use QPSK, if you use BPSK, the modulation schemes remain same. The probability of error remains same. The transmission technology we have changed. Earlier we have transported through a single carrier. Now we are transporting through a multi-carrier communication. Okay, so I think I have answered your question.
Yes, madam. Exactly.
Okay.
Madam, at the same time, madam, one more participant requested to us. Madam, could you please suggest any standard textbook for understanding of the OFDM?
Understanding of the OFDM. Standard
Yes.
textbook. So there are many textbooks on OFDM. MIMO OFDM wireless communication by Cho. I think the Cho is the best book. He explains very neatly each point, and also he starts from that basic digital communication modulation schemes. Okay.
Yes, madam. I
There are
hope
many
Sudhir
books.
Kumar. Yes, madam. Thank you.
Okay. If there are
Then
no
it's
doubts.
over. Yes, madam. No doubts.
Okay, then I'll quickly move to the next session.
Yes, ma'am.
Okay, just I think yes. So this is the visualization from one of the paper. You can see that how the OFDM works. If you are sending your signals through a single tap, I'm getting through a single carrier communication, I'm getting some information. But the same signal, if we are sending through a shower, right? This is a shower. So from the shower, each drop is coming out. So this each drop carries following a flat fading channel. But if you are continuously sending through a tap, it follows under frequency selective channels. So because of that, the probability of error is also going to increase. Your OFDM is nothing but a truck company which takes all their consignment into one single lorry. But when it is come to the OFDM, that is a single carrier. When it is come to the OFDM, it loads sub-components of your truck into different trucks and it transports the system very smooth way at same instant of time. This is the difference between OFDM to the frequency division multiplexing. And also what is orthogonality I said earlier, right? So you can refer this paper and you can understand very well how the OFDM works. I'm sharing this paper. So this paper is orthogonal frequency division multiplexing tutorial. So intuitive guide to principles of communication. You can go through these modulation schemes. So there are different modulation schemes. Everything is clearly explained and is also easy to understand. And also mathematical notations are given, very fancy notations are given. They are all very easy to understand if you want to work on your orthogonal frequency division multiplexing. Okay. And Kiran Mahi, how much time I have still?
Ma'am, for the first session, 1.5 hour, ma'am.
One
So
and a
we
half.
are
Okay.
1.5 hour, ma'am. So we have started at 2:15, no, ma'am. So 3:45 time is there for first session, ma'am.
Okay. I have one
Second
session.
session we started, ma'am.
I have one session or two sessions today.
2 sessions, ma'am. 2 sessions
Okay.
today.
Okay. I'm thinking that I'm only having one session, so I'm rushing
No, ma'am.
through each
No,
slide.
no, 2 sessions.
Okay. Okay. It's very nice.
Okay.
Right. So shall I go deep into the YFDM or can I go to the next scheme?
Yes, madam.
So I can go to the next session, right?
Yes, ma'am.
Okay. So the next modulation scheme is actually, I can show you a filter bank, or before I complete generalized frequency division multiplexing, I'll come back to filter bank. Okay, that will be nice. Right, okay. Just a minute. Okay, this is not my presentation. Okay, just start with some introduction because it takes some time to locate my PPTs. So why we are moving from 4G to 5G, right? So from OFDM and GFDM and other systems, actually my PPT is located somewhere, but I have taken some other PPT, no issue. So this OFDM and GFDM and what we have done in our laboratory also I can show you. We built a test bed for GFDM and we could able to publish some papers, a good number of papers on GFDM system. So just now we have seen the OFDM, orthogonal frequency division multiplexing. It is actually a kind of a multi-carrier system with the orthogonality between the subcarriers. Okay. So we have seen that actually these orthogonality between the subcarriers and also avoids intersymbol interference, and also we can accommodate more number of subcarriers, so we can save the bandwidth, and also it is easier to equalization as well. These are all the advantages we have just now we have seen in your multi-carrier communication. So um, so what is the main disadvantage in YFDM? If I ask you a question on what are the main disadvantages in GFDM, is the orthogonal carriers, right? IFFT and FFT. So this IFFT block and FFT block we are designing over here. Suppose IFFT block is generated with different multi-carriers. that is with sine 2 pi f naught of t, fn of t, and f3 of t, and so on and so forth. And in case at the receiving end, the FFT block also should able to generate the same amount of multi-carrier frequency. So from the transmitting end to the receiving end, if there is some value of a delta variation from one point to the other point, naturally it leads to an intercarrier interference. Okay. So this is that means we need a strict orthogonality between the subcarriers. So no one will guarantee you that your system will give you a strict orthogonality. Even if you maintain your electronics is perfect, even after the ambient temperature also it is working in a quite natural way, even then there is always a problem of inter-symbol interference and inter-carrier interference. And also the main problem is strict orthogonality. Okay. So then if you need, suppose some deviation is there in the transmitting frequency to the receiving frequency, that the sine of omega naught t plus delta of t. The delta of t is an additional phase. So this additional phase will lead to a problem of synchronization. Then is there any better method where we can go for, we can little bit leverage can be given for synchronization of your communication system, right? So that synchronization issue actually can be resolved using another new waveform. Just give me some time. I'm trying to join with my iPad one more time. So if I can check with sir, you have I joined with meeting ID, right?
Yes, ma'am. User, ma'am.
Join with user, join with a personal link name, right?
Yes, yes, ma'am.
Okay. What is the personal link name you have given? Is this Dr. VV Mani or VV Mani?
User, ma'am. It is renamed as user again.
No, now I am trying to join through my iPad.
Okay,
So
ma'am.
already I joined through laptop.
Okay, that name is user.
No, iPad name is not user. That name is user. You have given access to the user.
User, yes, ma'am.
Okay, now I am joining through iPad.
Okay, ma'am. Okay.
So what shall I write here? Join with meeting ID or join with the...
Anything, madam, no issue. You can join with ID or also you can join with the link.
Sir, can you repeat the ID one more time?
Sure, madam.
So because here I have some time, no, so I can explain in detail. But I don't know why it is not allowing me to do with my pad.
Madam, ID 870
870
4650
4650
3257.
3257. Okay.
Yes, madam.
I'm joining.
Passcode 12345.
1 minute, sir. 1 2 3 4 5. Yes. So can you see a new user join here?
What's the name, madam, for new user?
New user.
Please raise your hand from new user.
Sir, where can I see the raise hand?
In more, madam, there is. I think there is a Priscilla, Glory Priscilla. Who is that?
There are symbols are coming like join audio, start video, and share screen, participants, more. Yes. The more. But before I click that more, it is asking to hear others, please join audio.
Yes, madam. You can join with audio.
I could see the screen, what I am sharing in my other laptop.
Ma'am, we got it. I am giving a co-host, ma'am. Dr. VV Mani, NIT Warangal.
Yes, yes.
Yes, ma'am.
So now I can share my screen, right?
Yes, madam.
From both the sessions, I can share my screen.
Okay.
Yes, no issue.
But here I should stop sharing my screen from the another. Okay, I'm sharing. Start share. This will stop others screen sharing. Do you want to continue us? Okay. Okay, right.
It's visible, madam.
Yes, sir. Yes, sir. Yes, sir. Okay. Here, what I want to tell you is orthogonal frequency division multiplexing, right? OFDM. So as I said earlier, in my we have X case. We have X case, or this is my digital domain. This is my frequency domain, and X small x of n is time domain signal. Okay, so if x of n is given to your frequency band, that is your OFDM block, we know very well that is e power j 2 pi minus 2 pi k small n by capital N. This is the equation to compute your frequency domain equations. So here I can even open this one as cos 2 pi k small n by capital N with a minus sign. So it is sine 2 pi k n by capital N. And the summation of n equal to 0 to n minus 1 x of n. Okay. So these are the equations I am using. So when I am using these kind of equations, what I would like to say in OFDM, the major drawback in OFDM is, so I have to, for IFFT, this is at maybe if it is plus, so if I use plus, I said I would use K and the small x of n. This is my transmitting side. So this is my transmitting side. My transmitter, TX. Okay. So what about the receiver? In the receiver, so in the TX, I use IFFT block. I use IFFT block. In the this is at this is at transmitter, I use IFFT block. At the receiver, what I use, so at the transmitting end, I am using cos 2 pi kn by capital N, right? These are my two carriers, orthogonal carriers, cos and sine orthogonal carriers. At the receiving end, I receive x of n's. So I receive x of n. I implement my, sorry, I receive x of, what I receive? I give x of k. So I give x of k. So I receive x of n. This is my transmitter. So to these signals, I can compute the frequency domain. That is e power minus j 2 pi k n by capital N. This gives me back again x of k. That means the summation x of n and cos 2 pi k n by capital N minus sine 2 pi k n by capital N. This is my equation, right? So one is IFFT and another one is FFT. So this one is FFT. This one is my FFT block. So what I am saying, a strict synchronization is very much essential in communication. So strict synchronization in the sense, when I am transmitting my signal, I use cos. So 2 pi kn by n. When I receive my signal, I have to use the same cos. That is cos 2 pi kn by capital N. If you don't use the same cos and same sine, if there is a deviation from the cos and sine, instead of generating this cos, suppose my electronics is generated cos 2 pi k small n by capital N plus some 2 pi times maybe some n dash, because it is a phase, right? So I used a phase, 2 pi n dash phase, additional phase is generated. Then what will happen? So can you decode your signals? No, because always we do multiplication process, IFFT, FFT. I receive this kind of a signal. I'll multiply again with this kind of a signal. That means my original cos 2 pi k small n by capital N, this time is multiplied by cos 2 pi k small n by capital N plus some 2 pi into n dash, right? So if it is, if you don't have this 2 pi n dash, this simply can be written as cos square. That means 1 plus cos 4 pi. 4 pi k n by capital N, right? So this we can be removed using your matched filter. Only the constants will remain. From the constants, I can decode my data stream. I can decode my data stream. But because of your 2 pi 2n, it is not exactly cos A and cos A again. It is cos A into cos A plus B. So there is some residual point is coming into your communication. So this residual point will create lot of disturbance in my communication channel. So this is the major drawback, major synchronization issue in OFDM. So to avoid this major synchronization issue in OFDM, we are proposing a new stream. So we are proposing a new stream, proposing a new scheme that is. So can you see the?
Yes, ma'am. Yes, ma'am.
Can you see my new screen?
Yes, ma'am. Yes, ma'am.
Okay.
Proceed.
Yeah. So I am going to. That means you are controlling from your side, no? Karan Mai? Only one screen, only one person can present at a time, right?
Yes, madam. Only one person can present at one time.
One time. I cannot present from the both the sessions. So this option is available in WebEx. Okay.
WebEx, yes,
I can present through multiple devices. Okay. So no issue. Right. So we need a strict synchronization. So we need a strict synchronization. So why? But even then, we adopt OFDM only in 4G. Why we adopted 4G? Because of the availability of your FFT and IFFT filter banks. Right? So it takes time to turn on the cell phone. Like there are several disadvantages about OFDM. One is the sensitivity to frequency shift. The frequency shift just now explained cos 2 pi n dash. So this sensitivity will leads to a wrong errors. That is, it leads to a lot of probability of error is going to increase. And the transmitter and receiver need very strict synchronization. So, and also it is very crucial thing in communication. Okay. Now, there are several disadvantages about OFDM as well. That is, there is a large out of band radiation. If you look at the large out of band radiation, the power leakage affects the user in the near band. So the inside band, OFDM with 200 subcarriers, if you plot that equation of the power spectral density, then at the above we have power spectral density, it starts from 0, and as the frequency is increasing, it is going to minus minimum of some 20 dBs, minus 20 dB on the other side. So there is a large amount of power is deviated into the next bands, the other bands. This is one of the disadvantages in YFDM. But we will overcome these disadvantages in generalized frequency division multiplexing system. Okay. So this that is 5G, but this slide is actually very old slide, because that time even even the standards have not come up, and the researchers have worked on generalized frequency division multiplexing, and they started doing publications in GFTM, and they thought GFTM would definitely come as one of the standard for 5G, but finally they land up with only OFDM. because of some other disadvantages with GFDM. Even though it is spectrally efficient and we can save more bandwidth, but still, as I said earlier yesterday, we have to entirely shift your base stations to a new base station. It's not possible, right? The existing infrastructure, if you change a totally a new paradigm, then it takes a lot of money. You have a lot of economy has to be deployed onto the base stations. So it's not a feasible solution. So people thought again they come back to OFDM, but even then we need to understand what is generalized frequency division multiplexing system. So this generalized frequency division multiplexing system is also a kind of a multi-carrier system with circular pulse shaping towards the data. Anyway, in OFDM also, I said, when you are using a linear convolution, your data stream is going to stretch to a long data stream. But if you use a cyclic prefix, the last part is converted back into the first part that comes under a circular convolution. So this is also a kind of a follows a circular convolution. But here, what extra thing we are using for generalized frequency division multiplexing is we use some pulse shaping filters, a circularly pulse shaping filters towards your data. Okay, that means we are confining your band to your own band. We are not deviating from one band to the other band. Okay, so this confinement we are doing through some pulse shaping filters. Whereas in OFDM, as it is, we are transporting the data onto your multi-carriers. But here in GFDM, we pass the signal through a filter, that means a shaping filter. Then we'll port that data onto your multi-carrier communication. That is the difference from a GFDM to a OFDM. In a pictorial graph, I can show you the difference from a GFDM to a OFDM. And also we use a matrix notation. So the complexity of the system is also more compared to OFDM, because in the OFDM, using FFT and IFFT, I can show my entire transmitter and receiver. Whereas in GFDM, I have to use certain mathematics to show what is my transmission and what is my reception data stream constructed with the prototype filter. Okay, so there are some advantages because it takes lower out of band radiation, and also strict synchronization is very much essential in OFDM. So it gives some relaxation, not totally relaxed, but some relaxation of the frequency synchronization is there. And so because this is again connected with applications, Internet of Things, machine-to-machine communication, and other applications are present. No? So we always say this is more advantageous than the other one. Okay. Now, just look at the equations what we are using. A normalized P point DFT. So a normalized P point DFT. So if you look at this equation, e power j 2 pi, earlier I wrote k into n by capital N, right? So instead of k, instead of n, here we used p. That's only the difference. So a normalized p point DFT matrix, if you take e power j 2 pi mn by p, normalized with the root value of p, and p belongs to a natural integer. Okay, and we use sync x, that is a periodic sync function. We use a sync x. We know that sync x is sin pi x by pi x. Okay. Also, I can use a different mathematics. So a transceiver block diagram, how it is generalized. Here I don't think I can explain without using my notepad. Okay, I'll try to explain it. So in the GFDM transmitter, we take the data stream and translate this data stream into a matrix A. I'll show you in other slides because it is given in other slides. what is the matrix A, and then we wait for parallel to serial conversion. We also add a cyclic prefix and pass it through the channel. This A is your modulator. So what is that modulator? Modulator is a GFDM modulator. Okay. The same scenarios, again, convert into parallel to serial, add cyclic prefix and pass it through the channel and receive through the channel. That means remove your cyclic prefix and serial to parallel conversion and use a demodulator. That is, the demodulator is functioning on B and estimate your data symbols. So A is a modulator and B is a demodulator. How it is different from YFM, that is the concern for us, right? So here the subsymbols, what I am saying is total is equivalent to D. The D is K into M symbols. So your the data vector. So D means your data vector, this data vector. Okay, the small d, D of L. That means D cross 1 vector. This D of L is a D cross 1 vector. So this D of L of K plus MK, that is the mth symbol on the kth subcarrier. Because I said in your OFDM, to go back to the OFDM. Yeah, if you go back to the OFDM, here we use a mapper and a pilot insertion, guard insertion. After that, I use IFFT block, right? So this IFFT block is now taking in this format A. I take data symbols, D data symbols at a time. And this D involves what is the subsymbol notation? Mth subsymbol onto the kth subcarrier I am transmitting. Okay. So these D data symbols are actually, the total data symbols are actually K into M data symbols. K is my subcarrier index and M is my subsymbol index. I'll show you in another diagram how it is exactly looks. So if you look at the transmitter, we use some filters. So these are all the filter structures. There are M subsymbols here. So these M subsymbols are going through a transmitter matrix. So these transmitter matrix are going from 0. So first on first subcarrier, right? So MH symbol, right? So what is the difference from OFDM to GFDM is on K subcarriers and K subcarriers, we are sending the same data symbol 0, 0, 0. Again, next K subcarriers, I'm sending the first symbol repeatedly. And at the end, and an MH subcarrier, MH subsymbols, I'm sending on K subcarriers. I'll show you the exact diagram. So here, a prototype filter is used. That is G of G00. This is actually coming from a construction of your data stream A. So this prototype filter is actually a modular filter. Modular in the sense, suppose 4 into 2 equal to 8. So, but it leads to 10. Then the 2 coming back to 8, we will adjust into the 8 itself. Okay, that's why we come to the modulo operation. This is similar to your modulo operation. So this modular operation, G of N minus MK, this is a modulo operation. And your N is moving from 0 to D minus 1. So this is a frequency domain prototype filter is used. Then we'll arrange them in a matrix format. That is root D times W times WD into G. This gives the transmitted signal. Okay, maybe it's not clear in this mathematics, but I can explain you through other slides where you can easily understand through your diagrams, because a lot of mathematics involved in GFDM. So finally, a digital baseband filter, digital baseband signal looks like similar to IFFT here, similar to IFFT. Just scrolling down my cursor, e power j 2 pi k n by capital K. This is your IFFT block. Okay. So to this IFFT, what we have done earlier, just a data symbol is added. Now, in this case, to this IFFT block, we are adding a data symbol convolved with your filter bank. This is the filter. G of M is the filter. So this G of M is actually a circularly pulse-shaped filter. Here you can see the modulo of G, N minus Mk minus L over the D. Over the D, it comes back to the original value. So that is an additional precaution is taken onto your signal such that the out of band radiations it eliminates, and also it restricts your signal into a strict synchronization. So synchronization is deployed, even they are non-orthogonal signals, but they are restricted in some nature of a filter. Okay, so now, so the GFDM works with the channel and the receiver. So we can estimate the signals using MMSC, MMSC and MSC, MSC and zero forcing receivers. So that depends. The OFDM is actually, my subsymbols are equivalent to 1. My K equal to D data symbols. But if it is GFDM, K into M is equivalent to D. So K into M is equivalent to D. Here we use a Dirichlet pulse, a root-raised cosine pulse, and maybe the spectrally efficient pulses, where gives the better out-of-band leakage to your GFDM systems. So are there any doubts in the GFDM? Because it's purely a mathematical equations I'm dealing with. So if there are no doubts, then I'll continue with the presentation.
No.
Okay, madam.
Because it is too mathematical in the nature. So, I just skip all these mathematics. The performance, filter optimization and out of band, the filter with minimum the parameter settings. I just skip the power spectral density. So if you look at the power spectral density of a GFDM model using different filter banks, one is optimized filter, root-raised cosine filter, and Dirichlet filter, and your normal OFDM. So the normal OFDM is actually a blue color one. Okay, green color one. The normal OFDM is a green color one. But what we are trying to do in GFDM, by using different filter banks, filter shapes, we are trying to reduce the out of band radiations. That means the green color, we are trying to bring it down to the lower range. Green, we bring it down to the lower range. So that is happened through your RC, root-raised cosine pulse in red, as well as a Dirichlet pulse in even yellow, right? And RC filter with alpha equal to 0.5 factor, it is in the red color. They are much better than your normal OFDM scheme, and even optimized filter is giving a best performance out of all the radiation patterns, because it is restricted to only a certain band, whereas the other schemes, RC Dirichlet and OFDM, they are leaking into the other bands. Okay, and the symbol error rate using the different schemes for the GFDM is also analyzed. From suppose in this case it is OFDM2 with some factors of this data scheme, how the and also one more thing you have to I forgot to mention here, because naturally the GFDM gives a better performance than OFDM gives a better performance than a GFDM. But what for we are going for GFDM? Because of this localization. That means it is non-orthogonal, but still we can make your signals to decode perfect in nature. That's the only advantage with the GFDM. So what I want to say is, SCR performance, that is symbol error performance of GFDM and OFDM can be the same, but not exactly the same. Okay, this is what the observation of the researchers, the GFDM to OFDM. Okay. So this is the work done in my laboratory. So I can show you the test bed what we have developed for 5G communication in our wireless communication laboratory of NIT Warangal. You can see we have used transmitter and receiver using USRPs, the real-time communication. So, and we have built a GFDM modulator and a demodulator. And also we have measured the power spectral density of the transmitted signal as well as the received signal. The transmitted signal I and Q forms, the received signal I and Q forms, and their bit error rate is also evaluated. For pictures, to show the entire picture in one sector, we placed both the transmitter and receiver nearby. But frankly speaking, these transmitter and receiver kept it two different locations, and we have measured the distance. We have measured the communication link. So you can see the transmitter and transmitter I and Q transmitted data and their power spectral density, PSD. So this whole analysis, the baseband signals we have constructed in LabVIEW, and then it is ported onto the USRP. So from USRP, it goes to the channel, goes to the channel in air, goes to the air. So from the air, we start decoding the signals. So here, the exact timing is also important. So we have implemented new algorithms for timing synchronization as well as the carrier synchronization. So both the synchronization algorithms we have targeted, and also we could able to publish a good work based on this test bed. So this is my receiver. So we can see that the transmitter to the receiver, the transmission is started exactly at the 0th axis. But whereas the reception is started after certain time. But my decoding scheme, I don't know whether my decoding I have to start at 0 point or I have to start it at this point, because I don't know when my received signal is occurring to my receiver. So what exactly we have to do? We have to estimate this time. We have to estimate this null time. After estimating the null time, from that time onwards, we start decoding your signals. So this is what we have done in our communication laboratory. So my transmitted constellation diagram, my received constellation diagram, I forgot to mention at what SNR it is this constellation diagram looks like. And is also the power is increased. So when the power is increased, the constellation is coming across the localized to their respective positions. Even if you further increase the power levels, it is the constellation diagram is isolated to their independent locations. So we could able to see the outputs at the receiver. Okay, this is what a simple example, but I'll take you through my other slides where exactly what we have done for your for my VLC communication, for my GFDM communication. Okay. So Kiranmai.
Yes, madam.
So shall I continue or what's your opinion?
Ma'am, if you want to take break, ma'am, for 15 minutes.
Okay.
Because you are continuously giving lecture. Na?
Yeah. So today morning I started at 11. That is my regular class hour. So 11 to 1. And again it went up to 1:30. Some little lunch, and after that I came back to. But unfortunately, I could not use my pad. That's the bad thing. Otherwise, I can write something. I can show you the mathematics. What is hidden in my GFTM.
No problem, ma'am. No problem, ma'am. So take a 15 minutes break, ma'am. We will start after 15 minutes.
Okay. Okay. Thank you so much.
Okay. Thank you, ma'am. Thank you. Participants, please take 15 minutes break. Okay. Don't leave the meeting. After 15 minutes, the session will go on. Okay.
So he is one participant is very curious about 6Z, what 6Z looks like, right? So maybe I can throw some light on 6Z, how it works. So we are looking for new applications because there is a millimeter wave band is available, right? And even the lot of the spectrum is already overcrowded. So what next? How can I use my other applications into communication? So